about talking about heat and heat capacity and mixtures. And I think that a picture that we've seen before when we were like in grade 9 maybe is this idea of the kinetic molecular theory. And even if you didn't remember that phrasing, kinetic molecular theory gives this idea that there's molecules or particles that are moving around. You know, this kinetic energy. So I've got these particles. They're supposed to be in like a container, and they're zipping around. And when we talk about thermal energy, what we're really talking about is the total, and I'm going to emphasize that it's total kinetic energy, the total kinetic energy of all the atoms in a substance as they vibrate around. And I think that there's this thing because, at least when I was in elementary school, and from what I can see from my own children's notes, this idea that the substance has to be like a beaker full of water or something like that, or a balloon full of gas, you know, with particles bumping around. But you know, like it could be anything. This piece of eraser here has particles that are bumping around. They're jostling. They're vibrating, and just sitting here, this eraser holds thermal energy because its particles are vibrating. And there's a bunch of them. And if I add all that up together, that would be the thermal energy of that object. Every object has thermal energy. In fact, if you didn't have particles that were vibrating, that would be a really special case. You would have particles that aren't in motion. And to have particles that aren't in motion, that's actually very extreme. You know, you've probably heard about superconductors. Maybe you've heard about things being well below zero, super chilled temperatures, maybe even approaching absolute zero. Absolute zero is that theoretical point where particles stop vibrating. And when you approach the point where the particles stop vibrating, it turns out something wacky happens. You know, if this was a balloon, you know, all these particles vibrating around would be punching into the interior surface of that balloon, and that's what would keep the balloon inflated, essentially. It's actually the motion of the particles that keep it inflated, which is why when I buy a balloon at Party City and I take it outside, those particles slow down. What do you think happens to the balloon? Yeah?
It deflates.
It shrinks. It doesn't actually deflate. It doesn't lose any air. It shrinks. In fact, the lady, whenever I buy like a helium balloon for a kid's birthday party, and every once in a while I do, I'm going to confess. I know that helium's in short supply, and I probably shouldn't waste the helium on a birthday party, but every time I bought a helium balloon, the lady at the counter says, "Oh, I just want to warn you that it's going to look like it's deflating when you get it outside," because my kids' birthdays are in cold seasons. And then when it comes back inside again, it'll look like it inflates again. But this is why. This is exactly why that lady has to tell me that every time. Because otherwise, people that don't understand that are going to panic. They're going to think, "Oh my gosh, you just paid $20 for a balloon and it's going to die already." No, 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 no. Kinetic molecular theory. Okay. So this is something we should sort of know something about. Now, as you approach absolute zero, not only would the balloon deflate or look like it's deflating, I should say, the particles themselves actually condense right down. And something really weird happens. It's called a Bose-Einstein condensate. And that is definitely not something that I want to talk about today. But if you are interested in going down the rabbit hole of what happens when things reach ridiculously cold temperatures, look up what a Bose-Einstein condensate is. It's a different state of matter. It's not a solid, liquid, or a gas, but it's one of those extreme things that happens when you get really freaking cold. Okay, sorry for the strong language. But all right, so let's keep going with this idea. We're talking about the EK total, if you like, to use some of our macroscopic way of talking about things, because this is microscopic. This EK total is for all the particles, every single one of them. Now, the thing is, it's pretty much impossible. I won't say pretty much. It is impossible for us to zoom in and point a speed radar gun at every one of those atoms. Think about like an Avogadro's number worth of atoms and trying to actually like instantly measure all of their speeds and then cumulatively add up the kinetic energies. That's ridiculous. So we just kind of lump them all together and we say, well, that's heat energy. That's thermal energy. E subscript H. Now the chemistry people, actually a lot of physics people too, but I'm trying to match with our textbook and things. E subscript H would be heat energy. The chemistry people, most of them are going to use capital Q for quantity of heat energy. Doesn't really matter. chemistry and physics, you're actually speaking the same language with a different accent, okay? Doesn't really matter. Q, capital E sub H, same thing. And so I'm going to call that heat energy. My chemistry friends could also call it thermal energy. Thermal energy, heat energy, same, okay? I want to block out my page just a little bit. Temperature. This is one that people get mixed up with. People say, oh, it's hot outside. It's a high temperature. And I can see where in everyday speech you get those things mixed up. Temperature, though, is its own distinct thing. Temperature is an indirect measurement. Of the average, and I'm going to emphasize that, average kinetic energy of the particles in a substance. What do I mean by average? Well, look, if I took all those particles that were bouncing around over here and I kind of organized them and I listed them out and I said, okay, well, this kind of represents the kinetic energy of 4 of those particles. Obviously, 4 particles or 6 particles or whatever, that's a ridiculous cartoonish way of talking about it because we're talking about trillions and trillions of particles, right? But I'm just going to say I cherry pick out 4 of them. If I cherry pick out these 4, I could figure what the average kinetic energy would be for those guys. And that's what I'm talking about with thermal energy. It's a measure of an average. Now, sorry, not thermal energy, temperature. Temperature is a measure of the average. Thermal energy is the total energy in joules. It's actually measured in joules. Temperature is an average measurement of energy, and it's not measured in joules. It's measured in sort of an indirect way. And we know probably what units we use for temperature. What is it? Degrees Celsius oftentimes, right? We're going to talk about that just down here just in a second. But I just want to make sure it's really, really clear that we're talking about a mean. Average means mean, a mean value. But we're not measuring temperature in joules. And then in terms of the variable, we're going to use capital T for temperature. Now, if you want to make a positive statement, this is not in joules. Heat energy is measured in joules. But that begs the question, if it's not in joules, what do we measure our temperature with? And so obviously I have a little table here. But one of the ways that we measure temperature is in Celsius, degrees Celsius. I've heard people say centigrade. Celsius is the last name, and it's a capital C for Celsius. And here I've got a thermometer. Here's 0 degrees Celsius. All the way up here, I've got 100 degrees Celsius. And people say, well, what's the distinction? Why would I bother with 0 and 100? And people always say that Celsius is based on pure water. It's based on what pure water does. What does pure water do at 100 degrees Celsius? Yeah. It boils. Yeah, this is the boiling temperature. Boiling point of pure water. And what happens at 0 degrees Celsius? Yep. Freezing point, yeah. Freezing point of pure water. And people say, well, why would you choose water as the standard? Well, our planet's mostly made out of water. People say, well, why wouldn't you use salt water? The ocean's mostly made out of salt water. Well, maybe you know this, maybe you don't. If you're a cook, you know this. If you add more salt, doesn't that change the boiling point of water? And if you add a lot of salt, doesn't it change the boiling point of water a lot? And the salt concentration of the world's ocean isn't uniform. And so that's not a good standard. Pure water, that's pure. We've removed all the salt. How can you purify water? Well, you can boil salt water, catch the drippings of the condensation. That's pure water. This is something we've been able to do for ages. That's called desalination. That's how we get drinking water from the ocean. That's a very important process. But having pure water as the standard, incredibly important on a water-based planet like ours, right? In fact, we're water-based life. So to talk about it, that's fine. Now, I'm not going to talk about Fahrenheit really today. You can look up a YouTube about what Fahrenheit is all about. Fahrenheit essentially is about the temperature of life. And Fahrenheit was based around the temperature of healthy animals, which makes sense if you're going to base your economy and your science on agriculture. Okay, and if you want to go down a rabbit hole, Minute Physics is a great YouTube channel that explains what's the point of having Fahrenheit. That's a great conversation. I don't want to talk about that right now because it really isn't a metric unit. I want to stick with metric units or SI units, System International. So the other one that we want to focus on is Kelvin. This is capital A or capital K, named after Lord Kelvin, but we don't write degrees Kelvin. We just say Kelvin. Okay, so degrees is reserved for Celsius, but this one is based on the absolute zero concept. Now, what's the absolute zero concept? Well, this is the temperature. So I'll say, which is the temperature at which, we were talking about these vibrating particles. At absolute zero, it's the temperature at which particles stop vibrating. Altogether. Okay, so a total stoppage of particle vibrations. Well, how do we relate Kelvin and Celsius then? Well, if I talk about 0 degrees Celsius, it turns out that 0 degrees Celsius is equal to positive 273.15 Kelvin. They're offset by 273.15 Kelvin, or 15 degrees. People say, well, why did they choose that weird number? Well, we didn't choose that weird number. Nature chose it for us. 0.15. Nature chose it for us. Temperature of boiling water is what it is, right? That's what we base this system on. The temperature at which particles stop vibrating is how cold it is. We didn't choose it. The universe kind of chose it, okay? It's just the way things are. And we can talk about what gives rise to those patterns, but that is the way it is. Now, if I were to say 0 Kelvin, and it kind of looks like somebody saying, okay, but 0 Kelvin, okay, is equal to negative 273.15 degrees Celsius. Now that's kind of relevant for us because things can't get any colder than that. You can't get colder than particles not vibrating. So if you're reading something about a superconductor getting down to a really cold temperature, typically, maybe minus 40 degrees, minus 100 degrees. Actually, minus 40 isn't even that cold. Minus 150. If anybody ever says that they got their superconductor down to minus 300 degrees Celsius, fake news, right? It's not physically possible, right? So we want to make sure that we have an understanding of what temperature is and the fact that there actually is a limit to how low Celsius can go. And the limit's defined by particles just not vibrating anymore. You can't unvibrate, so you can't go lower than negative 273.15. That's it. It's a limit.
Vibrating back in time.
Yeah, vibrating back in time. All right, so here's another thing about this. If I say 1 Kelvin, and I just talk about how big is 1 Kelvin, so I'm going to put absolute values around it. It feels weird to put absolute values around it, but I'm just talking about how big a Kelvin is. A Kelvin is the same size as a degree Celsius. Now, we actually did choose that. The reason that we chose 1 Kelvin, like the increment of a Kelvin, to be the same size as the increment of a degree Celsius, is because it made all of our formulas still work. We didn't have to rewrite all the formulas, right? And people say, well, why is a degree Celsius the size that it is? Why choose that bigness of a unit? Because it divided evenly into 100 between 0 and 100 degrees Celsius. That's all it is. We just wanted to have a 100-point scale, a decimal-based scale between freezing and boiling. So we split that up into 100, That's how big a degree Celsius is. And then we wrote a whole bunch of formulas. And then we'd already written all these formulas for chemistry and physics and other things, biology. And we decided we're not going to change the size of a degree. We're going to just make the size of a Kelvin match the size of a degree, because that makes sense. We don't want to make more work for ourselves. That's just sensible. But if that's the case, we could say, therefore, if we raise a substance, heat it up. If we raise a substance by 12 degrees Celsius, we also raise it by how many Kelvin? Yeah, 12. Okay, and I don't think that's like earth-shattering or anything. Just makes sense. Now, if you want to pick on history a little bit, I don't even know if this is true or not, but I'll zoom in on it. Supposedly, James Joule took a thermometer on his honeymoon because he wanted to measure the temperature of waterfalls at the top of the waterfall and at the bottom of the waterfall. Can you imagine going on a waterfall holiday? It's your honeymoon. You're like, let's go see the sights. And your brand new spouse brings out a thermometer to measure the temperature at the top and the bottom of the waterfall. Like, honestly, I could see myself doing that, but maybe like in a sneaky way. I might not say anything to the wife about that one, but I might just sneak a thermometer and check. He was hoping to find that the thermometer was warmer at the bottom than at the top. The particles would be moving more at the bottom than at the top. What do you think he found?
Same.
It was the same. Yeah. It turns out that those perturbations in the particles, it's not going to pick up a temperature change. Okay. Now, whether or not that's even a real story, or if it's just something that people told years after that, there's this name for stories that can't be substantiated. They're called apocryphal tales, apocryphal stories. So this is an unsubstantiated story as far as I know. I don't know if that really happened or not, but wouldn't that be a thing, right? Like take like a thermometer on your honeymoon.
So interesting.
So yeah, it says that it was reported 35 years after the honeymoon. That's probably a good time to start making up lies about somebody, right? Anyway, I feel like if his wife had claimed it like at a dinner party like the next weekend, then we'd believe it. Okay. Let's take a look at these beakers, because I said that this is going to feel a little bit like chemistry, so I got my chemistry equipment here. And let's fill this beaker with water. Fill it up with water, and here I'll illustrate that it's got water in it. You can add this little water line in there. It's all filled up with water. And this water is 95 degrees Celsius. Like a cup of tea, just came out the kettle. 95 degrees Celsius. Then we're going to put another container of water. Same amount of water, mind you. But this water is at 30 degrees Celsius. And I feel like this is one of those magic tricks where you're like, what happens next? We're going to take this water and we're going to pour them together.
Yay.
Notice the fill line is higher now. Okay. If you're not familiar with it, you call it the Phillip line. If you know each other well, you call it the fill line. So I got the fill line up to here, up to the fill up line. And I got to figure out what the temperature of this water is going to be. And there's some people that probably could figure this out in a hurry, but I want to think about some other things too. And so I want to make myself a little table. I'm not even going to bother with a ruler. You can make yourself some wiggly lines here. And I want to talk about temperature, because we had some definitions at the top of the page here. Temperature, and I want to talk about heat. Well, which of these has the highest temperature? Yeah?
First speaker?
Yeah, first speaker. This is the highest temperature. So that's the highest temperature. Anybody want to tell me, while we're on the topic of temperature, if this is the same amount of water in both, what's the temperature of the mixture going to be? I bet you there's somebody with a calculator that's figured it out already. What do you think? Yeah? It's not 75. Yeah,
65?
not 65. You're getting so close. We're just dancing around it. What do you get?
62.5.
62.5. How'd you get it?
Add them together, divide by 2.
Yeah, look, you just added them up, divided by 2, found the average value. Ooh. Now, that only works if it's the exact same substance and the same amount, right? If there was more of one than the other, then the average would be thrown off. Okay? So this is a super special case that we can do that. All right, so having said that, which one is the lowest temperature?
The other one.
Come on. First, second, or third? Which one's the lowest temperature? Yep. Second one, yeah. Lowest temperature. I guess this means this one's the medium temperature. Mid. It's mid. Okay? That's temperature. Heat, though. Which one has the least amount of heat? Before we do this, let me go back to look at what heat is. The definition of heat is it's the total kinetic energy of all the atoms in a substance as they vibrate around. That's heat. Which one has the least heat? Which one has the least kinetic energy for the total of all the particles? Yeah.
Would it also be the middle one?
Yeah, it is. This is the lowest heat, or the least heat. Least heat energy, least thermal energy. I'll put that in brackets because it's synonymous. Okay, the least thermal energy, the least heat. Which one has the most heat energy? Remember, most heat energy would be the one that has the most total kinetic energy. Yeah, it actually is the third one. You know, it's a 50-50 shot. Half the time people get it wrong. But I mean, people are always wondering, like, there's a trick here. Do you know why it's the third one? Yeah, he says this is the total energy of those two heat energies combined would make the heat energy here. Remember, all the particles that were in those two containers are now in this container vibrating around. Sure, the average is lower, but the total is the sum, right? So this one has the most thermal energy. That's perfect. That's totally the right understanding. Most thermal energy, most heat energy. And I guess this one would be the medium heat energy. So it's such like a mama bear, papa bear, baby bear kind of situation, you know? And really to drive it home, I one time saw like one of my favorite physics professors teaches a physics course for non-physics majors. He was talking about taking a teacup full of, or coffee cup full of hot water and a swimming pool. And that fellow lives in California, but it could be true here too. I got a swimming pool in my backyard, and any given time, it might be the case that my pool is 25 degrees Celsius. Now, actually, my wife likes to keep it closer to 30 because, I don't know, she likes a big hot tub. So, sometimes I like to heat it up like a couple days a week because I don't like to run it at 30 degrees every day of the week. That's kind of pricey, honestly. But let's just say a 25 degrees Celsius swimming pool, a 100 degrees Celsius cup of coffee, which is mostly water, honestly, right? Which one has the most heat? Remember what the definition of heat is. It's the total kinetic energy of all the particles. Yeah. Yeah, the pool. Don't you think that pool has like 10,000 coffee cups in it? If this pool has 10,000 coffee cups, sure, the temperature of the coffee is like 4 times more the temperature of the pool. But there's way more than 4 coffee cups worth of particles in this pool. This pool has a lot of kinetic energy in it. And this is a good reason for why when you live near a large body of water, like if you live by the Great Lakes, all that water holds a ton of energy. And it's just sitting there like a great big hot water bottle. And so there is like a lake effect that keeps people that are right by the water's edge just slightly warmer. And if you're a couple kilometers away from the Great Lakes, the temperature drops off by like a degree or two. But that huge energy source actually keeps you warmer in the winter, just a little bit, and in the summer keeps you just a little bit cooler in the summer. And there's more complicated things than that, but that water holds on to a lot of energy. We'll talk more about how water holds on to energy in a bit, but coffee cup versus swimming pool, there's most heat energy in this. Remember, I'll just make the comment that heat energy is EK total for the particles in the substance. Now this last little bit here, I'm just going to sneak right into the corner and look at this little illustration. And there's this thing that when I was a kid, I was amazed by this. I did this in, I would say, grade 5. My teacher was trying to teach us about the senses, but also how you couldn't always trust your senses and how your senses aren't necessarily a good basis for scientific observation. Sometimes they are, sometimes there aren't. A good indicator of when it's not a good indicator that's not always a good choice for observation in science is temperature. And you can try this at home, but grab yourself a couple of containers of water, put hot water, not so hot that you're going to burn yourself, but hot water straight out of the tap into one container, and put ice cold water into another container, and then take a third container and make it be like room temperature water. And what you're going to find is, well, you tell me, if you move your hand from the cold water into the room temperature water, how's it going to feel? Yeah, it feels warm. If you take your hand from the hot water and put it into the room temperature water, how's it going to feel?
Cold.
It does. It feels cold. It turns out that your sensory system doesn't actually measure temperature. Your sensory system measures the difference in temperature. So you can feel when you get cooled off, you can feel when you get heated up, but you can't really feel hot or cold very well. And that makes sense. I can tell when I'm getting overheated, when my temperature is transitioning to a hot state. I can feel when I'm cooling down and I should put a blanket or a sweater on. I can't, once I get chilled, you ever notice that when it's a cold day, once you get settled into being cold, you're okay. If you ever go swimming in Lake Ontario, oh my gosh, when you go swimming in Lake Ontario in August, it's cold in August. It's a cold lake. Everybody always says, oh, the secret is you get in there. And once you're in there for like 5-10 minutes, you don't feel cold anymore. No, man, you're still cold. You're just not feeling the temperature changing anymore. That's what this is, okay? You can say you've gotten adjusted, you can say you've gotten acclimatized, or you can just say, hey, my sensory system measures changes in temperature, not temperature. Everybody cool with that idea? All right.